Assalamu alaikum everyone. Our first lecture is on recurrences, and this is the list of topics. First, we define what is recurrence relation, and then we go through three different methods of solving recurrence relation. The first one is the substitution method, then the recursive tree method, and finally the master theorem method. These are all different methods of solving recurrence relations or recurrence equations. We shall take many examples, especially with the master theorem. It has many examples, and then at the end we'll look at some exercises which you can try on your own. So what is a recurrence relation? The computational cost of a divide and conquer algorithm, as we saw when we look at merge sort in the previous lecture, is usually expressed as a recursive function, usually in this general format. So T of n is equal to a Tn over b plus d of n plus c of n, where a here is the number of subproblems, each of size n over b. As you remember, in the divide and conquer, we divide the problem into subproblems. So assume we have a number of subproblems, that is the meaning of A. And of course, when we divide the subproblem, we are basically dividing the input size. Okay, so if we divide the input size by B, then its subproblem will be of size n over B. And this is where the B comes from. Okay, notice that the B doesn't have to be equal to A. Sometimes they are equal, but sometimes they are not. Now dn is the cost of the division. How much does it cost to actually divide the original problem into the subproblems? And then finally, cn is the cost of the combining the different solutions so that you obtain the solution to the original problem. Alright, now as you can see, we are defining Tn in terms of t. Okay, the running time function t is being defined in terms of itself, and that is what we are trying to solve, because normally we will want, so in general, the runtimes of most recursive algorithms can be expressed as recurrences, as you can see above. The challenge. Now, recurrences are often easy to define because usually they mimic the structure of the algorithm, as we saw in the case of merge sort, but they do not directly express the computational cost in terms of n. As you saw on the right hand side, we still have the function appearing on the right. What we will want is for this t on the right to completely go away, so that we have everything as a function of n. N or n square or n cube or some function of n, but without repeating the t itself. This is basically the challenge, or what we are trying to achieve with solving recurrence relations. So that's what I'm saying here, that we want to remove the self-recurrence and find a more understandable form of the function, purely in terms of the input size, n square, n cubed, n log n, and so on, but without t appearing on the right hand side. So as I mentioned in the beginning, there are three approaches to solving the problem. One is the substitution method. The substitution method, as we shall see, require you to guess the solution and then prove that your guess is correct. This may sound as a strange approach, because actually to guess the solution, it will require some experience. But we shall see there are ways to actually find a possible solution, which is actually the second method. The recurrence tree method, we saw it in the last lecture, where we tried to solve the recurrence for the merge sort. We basically expand the tree and we were able to eliminate the t from the right. So that is another method. But actually, the recursive tree method is not full proof on its own. It's not assumed to be a complete proof. After you get the recurrence, rather after you get the result from the recurrence tree, you still have to prove it using substitution. So in other words, this recursive tree method can usually be used to find a possible solution. Instead of guessing, you can actually use the recursive tree to find the solution, and then later on you use the substitution method to actually prove it mathematically. And the last method is the master theorem. Master theorem actually provides a kind of formula that can easily be applied to deduce what is the running time given the recurrence relation. So this is the method we're going to look at last. Okay, but it is not applicable to all recurrences. It is applicable only to recurrences of this form. So where you have on the right a Tn over b plus Fn. So as you can see, the Dn has been removed. If you can represent it like this, if you can combine the Dn, the cost of the division, and Cn, the cost of combination, into a simple function of n, then you can apply the master theorem. Okay, so we start with the substitution method. As I said, this involves guessing the solution based on your experience, and then using mathematical induction to show that the solution is correct. So we're going to take a couple examples and see whether you can guess the solution, and then we show you how to actually use the substitution to prove the guess. So it says here, after, of course, we know the idea of proof by induction. You have the base case, and then you have a hypothesis. So in the hypothesis, you're going to assume the answer is true for some value less than the original n. And then you now to prove based on your hypothesis that actually the result is true even for the n. Okay, so this is why it gets the name substitution, because you're going to substitute your hypothesis back to the original equation, and then to see if it will work even for n. Now, the advantage of substitution method is that, of course, it works well when the solution can be guessed easily. If you can easily guess the solution, then it is very easy to prove using substitution. Essentially, it is proof by induction, which I'm sure you are familiar with even from your other previous courses. But the problem with it, as we said, it requires some experience for you to be able to guess a correct solution. So we're going to take examples, see how this works. Suppose you have a recurrence like this: Tn equal to Tn over 2 plus d. What do you think will be the running time of this function? So the way to look at this is to look at what is actually happening. You came in with a size of n. Okay, so the running time with respect to n is the same as the running time with n over 2. Okay, so like you are dividing the input by 2 and adding only a constant value. Okay, so it says here, have the input, then a constant amount of work. So think about this. Which algorithm in your experience work like this? If you think very carefully, this is exactly what binary search will do. Yani you come in with a size, let's say 64, an array of size 64, and you're trying to search for an element. Of course, in binary search, the assumption is the elements are sorted. So what you do is you find the middle index, and then you try to locate the element in the middle index and compare it with your target. So obviously, this locating the middle element and comparing it to see whether it is equal to your target will take a constant time. So you can assume that is d. But now, assuming you find that your target is in the right side, not on the left side, all you have to do is repeat the same thing, but this time with half the input. So whatever time it takes to find the element in half the input, plus this constant work that you did in doing the division and doing the comparison, is basically the running time of your original algorithm with the size of input as n. So this is essentially the recurrence relation for the binary search. So what do you think is the running time of binary search? Can you now guess? Any guesses? Normally in a normal class I will ask and wait for students to provide the answer. But unfortunately here I will not receive any. So I'll just tell you the answer straight away. So as I said, it's similar to binary search, and you should know by now, at least if you have done your assignment number 1, you will know that the running time of binary search is log n to base 2. So we are saying the running time of this Tn is big O of log n to base 2. Right? So that's the guess. And that is the first step in the substitution method. We have to guess an answer. And the next step now is to try and prove that that answer is actually correct using the substitution method. And this is what I'm going to try and show you. So we need to prove that Tn is big O of n log n. Okay, we need to prove that the assumption here, or the guess here, is correct. So we do this using induction. Okay, we need to make a hypothesis with a smaller value of n, and then show that the hypothesis is also true even if we go to n, even if we extend the input size to n. Okay, so assume it is true, yani that Tn is indeed log of n to base 2, big O of a log of n to base 2 for some particular value of n, let's say k, where k is less than n. Okay, so this is a hypothesis. Suppose that Tn is big O of log of n to base 2. Assume that is true for some k where k is less than n. Then now we need to prove that it is indeed true even for n itself, not only for a k less than n, but even for the n itself. This is usually the process. So let's try it. So our Tn is Tn over 2 plus d, and based on our assumption, T of k, where k is less than n, is big O of log of k to base 2. Now we need to show that Tn is indeed big O of log of n to base 2. In other words, if it holds for k less than n, it also holds for n itself. Okay, so what we say is, from our assumption, you see we are assuming that the result is true for any k less than n. If it is true for any k less than n, definitely it is true for n over 2, because n over 2 is less than n. And therefore, Tn over 2 is big O of log of n over 2 to base 2. This is by our hypothesis, or by our assumption here. So if that is the case, then all we have to do is substitute this value that we got into the original equation, replacing T of n over 2 with this. But before that, can we represent this big O of log of n over 2 to base 2 as some function of Cgn? Of course we can, because from the definition of big O, we know that big O of Gn is the set of all functions Fn for which there exist positive constants C and n naught, where Fn will be less than or equal to Cgn for all n greater than n naught. And therefore, instead of leaving this right hand side as big O, we can actually replace it in this form, less than Cgn, where Gn is log of n over 2 over to base 2. So from the definition of big O, we can say that this Tn over 2 is less than or equal to C times our Gn, which is log of n over 2 to the base 2. So it is at this point that we now need to do the substitution. In our original equation, remember our target is to prove that Tn is bigger of log of n to the base 2. So we want to eliminate this Tn over 2 from the right hand side. And since we have now represent that Tn over 2 purely in terms of n without the t, we can substitute it back in the original equation, and that should eventually allow us to see what is on the right of this equality. Okay, and then we'll be able to show that Tn is indeed bigger of n log n to the base 2. All right, so continuing, we do the substitution now. See, instead of saying Tn equal to Tn over 2 plus d, we will replace this with less than or equal to C log of n over 2 plus d, because this is what we just saw from our hypothesis. Our hypothesis says Tn over 2 is less than or equal to that. So if you replace Tn over 2 with that, then the equality here becomes less than or equal to. And now all that is left is some simplification to try and make this right hand side to be in the form we want. And this is the form we want. We want it to be in the form of log of n to base 2, or big O of log of n to base 2. So the first step is to see if we can make it in the form of C log n to base 2. If we can do that, then we will say it is bigger of that. Now here we just need to use some simplification. Obviously, we know the law of log. It says log of a over b is the same as log of a minus log of b. Therefore, this can be simplified into C log of n to base 2 minus C log of 2 to base 2, okay, plus the d. Okay, so just to make sure you understand what we are saying, I am saying there's a property of log that says log of a over b is the same as log of a minus log of b. Doesn't matter the base, whatever the base, log of a fraction like this can be written as this. So that's all we are doing here. Log of n over 2 can be represented as log of n minus log of 2. But since we are multiplying c here, we have to multiply it through. So it's c log of n to base 2 minus c log of 2 to base 2. But we also know that log of a to base a is always 1. Therefore, this is actually 1. So we can say this is log of c log of n to base 2 minus c plus d. Now, if you notice, this is actually what we want. We want our Tn to be less than or equal to c log of n. Because if it is that, then by definition of big O, our Tn is actually going to be log of n to base 2. Okay, but the question is, we still have these two terms, minus c plus d. Under what condition can we say that this is simply less than or equal to c log of n to base 2? Under what condition can you say this term is less than or equal to this term? It will only be true if this c that we are subtracting is much bigger than d, okay? Because then we are subtracting more than we are adding, and therefore the result will be bigger. Yani this term without this the subtraction of c and the addition of d will be greater or equal to that. If what? if C is greater than D. Okay, so, and this is what we want to reach. Actually, that's what I have here. I said this is less than log of n to base 2, or C log of n to base 2, provided C is greater or equal to D. Provided C is greater or equal to D. Alright? Now, if we are able to represent Tn to be less than C log of n to base 2 for some positive C greater or equal to D, this is exactly the definition of big O. Yani Tn will be big O of log of n to base 2. And that's our target. Yeah, so that's the conclusion here, that we have been able to prove that indeed our Tn is bigger of log of n to base 2, because we managed to find a C which is greater than D, which is a positive. Okay, we have found D which is positive, for which Tn is less than or equal to C log of n to base 2. Okay, this is example 1. Let's take another example, solving recurrence relations using substitution method. So here Tn is equal to Tn minus 1 plus n. Any guesses? What do you think is the simplification of this recurrence relation? Tn will be bigger of what? So again, if you examine this closely, we are doing n operations and then calling the recurrence relation again, this time with almost all of n except we subtract 1. So again, when we call it with Tn minus 1, is going to be Tn minus 2 plus n minus 1. So we are doing n work plus n minus 1 work plus n minus 2 plus n minus 3 and so on. This of course eventually will be 0, and T of 0 is constant. But if you keep adding this term n, then n minus 1, then n minus 2, and so on until you reach 1, what do you think you are doing? What is the running time as a polynomial of n? Clearly this is going to be n squared, because it's like we are multiplying n by itself. Okay, almost n by itself. Okay, we know, for example, from adding the sequence 1 plus 2 plus 3 and so on until n, we will have a function in terms of n squared. Okay, so clearly this recurrence relation is going to be big O of n squared. This is the guess. Okay, so this is what we are saying here, that at each iteration this recurrence relation does a linear amount of work, n is linear, and then reduces the size by only 1 at each step. Therefore, the best guess for the running time of this algorithm is actually big O of n squared, as I explained. So once you are able to guess the solution, the next step is try and prove it using induction. Okay, so we're going to assume again a hypothesis. Suppose that Tk is big O of k squared for some k less than n. So this is our hypothesis. Can we, based on this hypothesis, prove that Tn is indeed big O of n squared? Well, instead of taking any arbitrary value k, let us use the value we have here. You see, in the previous example, instead of k, I took n over 2. Okay, n over 2 definitely was less than n. So similarly here, instead of using k, we're going to say, well, n minus 1 definitely is less than n. So if it is true for any arbitrary k less than n, definitely it is true for n minus 1 as well. And therefore, we can say that this implies that Tn minus 1, so where we take our k to be n minus 1, will be less than or equal to some constant c times n minus 1 squared. This is what our hypothesis will imply. Okay, so the next step, therefore, is to substitute this hypothesis back to the original recurrence equation. Instead of Tn minus 1 here, we will have less than or equal to Cn minus 1 square, and then plus the n here. and then try and simplify it to see if we can have it in terms of Cn square. Because if you can have it in Cn square, then it is big O of n square. This is basically the idea of substitution. So to show that Tn is equal to big O of n square, we need to prove this, as I just said. So let's proceed. So instead of Tn minus 1, we will say substitute it with Cn minus 1 square based on our hypothesis. Just replace the equal with less than or equal to. Now if you expand this, this is n square minus 2n plus 1. If you expand this quadratic equation, n minus 1 square is n square minus 2n plus 1. And if you multiply by the c here, you will have cn square minus 2cn plus c plus n. So the question is, under what condition can we say this expression is less than or equal to cn squared? Because remember, that's our target. If we can represent it like this, Tn less than or equal to Cn squared, then we can say Tn is big O of n squared. So under what condition can we say this is equal to this? So let's proceed and see. So this term which I cycle here is called residual. We want to see if we can eliminate it so that we have just Cn squared. Okay, and clearly the expression here, Cn squared minus 2Cn plus c plus n, will be less than Cn squared only if this residual term is negative or equal to 0. If it's less than or equal to 0, then on the right hand side here we are not subtracting anything, but here we are subtracting something. So therefore this term where we are subtracting something will be less than the term in which we are not subtracting anything. But the question is, for what value of c will this be negative? So this is what we are going to try and simplify this inequality to find the value of c. Provided we can make that value of c to be positive, then our inequality here will be true. Okay, so let's proceed. Suppose you move n to the other side of the inequality, it will become minus n. Now factor out the c. So c is factored out. Here we are left with minus 2n. Here we are left with n. Less than or equal to minus n. Suppose you first of all multiply both sides by minus 1. Then what you have is c 2n, because minus 2n times minus 1 is 2n, minus 1, because plus 1 now, if you multiply by minus 1, it will be minus 1. Okay. On the other side we have n, because minus n times minus 1 will be n. But remember, if you multiply by minus for an inequality, the inequality is going to change. So this is actually going to change to greater or equal to. If you multiply both sides by minus 1, this is what you have. So from this one now, if we divide both sides by 2n minus 1, then we will have c less than or equal to n over 2n minus 1. Okay, let's try to eliminate the n so that we will just have a constant value. Okay, so to do that, let's divide top and bottom by n. So n divided by n will give you 1. 2n divided by n will give you 2. And then we will have 1 over n here. The question is, for what value of n will this be positive? For what value of n? Of course, remember, n is always positive. Okay, we are always looking at the top right quadrant for our values of n. So we are only looking at this side. So the smallest possible value of n is 0, 1, 2, and so on. So the question is, for what value of n will this be true? Obviously, we cannot say n is 0, because then this will not be defined. It will be infinity. So suppose it is 1. If you take n to be 1, we will have 1. So 2 minus 1 will be 1, and 1 over 1 is 1, which is positive. And actually that's the biggest value you can have, because now if you take 2 as the value of n, then this is going to be half. And 2 minus half is 1.5. And 1 divided by 1.5 or 1.5 is definitely less than 1. Okay, so these values will keep decreasing. 1 is the maximum value you can have, but it is not negative. It is some fraction, which is fine. See, all we want it for it to be a positive number, not a negative number. All right, so it means therefore if we take n to be 1, then we will have c to be greater or equal to 1, and it will satisfy our inequality here that we began with. So it means therefore that our inequality Tn less than or equal to Cn square will hold provided n is greater or equal to 1 and C is greater or equal to 1. And if that is the case, then by definition of big O, we have proved that Tn is big O of n square, because we were able to find positive constants C and n for which the inequality is true. The inequality Tn less than or equal to Cn square is true. So this is basically how you prove that recurrence relation that you guess is true using the method of substitution. You have to make a hypothesis with k less than n, and then make the substitution and prove that it is also true for n. Now let's look at the second method of solving recurrence relation, which is called a recursive tree method. So like I said, the recursive tree method is not really accepted to be a rigorous proof. Usually it only guides you to guessing the solution, so that once you have a solution, then you can now use the substitution method to prove it. Or you can use the master theorem, which we shall learn later, to prove it. So that's what we are saying here, that guessing the answer of a recurrence relation can be difficult, or at least to require some experience. For example, if you look at these two recurrence relations, it is really very difficult to guess what they are going to be. 3Tn over 4 plus Cn square. Okay, what is the big O of this? And similarly for this one, Tn is Tn over 3 plus 2T2n over 3 plus Cn. This is very complex. You cannot really guess it. So in that case, we try to apply the recursive tree method to help us. And that's what we're going to do. Actually, I already showed you one example last time, which is the recurrence relation of merge sort. We did solve it using recurrence tree. So we're going to try another one as our second example. So the recursive tree approach, it involved drawing out the cost of the tree at each level of the recursion, and then sum up the cost of the levels of the tree. Now this involves finding the cost of each level with respect to the depth, figuring out what is the depth of the tree, and then figuring out the number of leaves you're going to have. The last level, you have to find out how many terms are going to be there, or how many leaves are going to be there. Okay, if you can do this, then you will be able to estimate the running time. So once you do that, you still have to verify your answer using the substitution method or using the master theorem method. So let's try and solve it, especially for the first example there. So this is our example. Suppose Tn is 3Tn over 4 plus Cn square. can we solve this using the recurrence tree? So recurrence tree involves expanding the tree a few times to see the pattern. Once you see the pattern, it will allow you to know what is the cost of each level. It will allow you to find the depth D of the recursion, and then it will allow you to know how many leaves are going to be in the last level. If you can know these three things, you will be able to estimate the running time. Okay, so this recurrence relation can be represented as a tree like this, where we make this to be the root cn square plus, here we are doing 3tn over 4. So we can have a branch for each of the sub-problems. There are 3 of them. So we have tn over 4, another tn over 4, another tn over 4. If you add all of this plus the cn square, they will give you the same cost as your original running time function. Now you're going to repeat this a few times. So we're going to try and see now what is the value of tn over 4. So all you have to do is go back to the original function here. We know what is running time if we have just the n. The question is, what is it if we replace n with n over 4? Clearly it's going to be 3. So essentially what we are saying, wherever you see n here, change it to n over 4. So we have 3 t. Now instead of n, we will say n over 4. So n over 4 over 4 is basically n over 16. Okay, n over 16. If you like, n over 4 square. Plus c n over 4 square. Remember, wherever you have n, change it to n over 4. So we will have n over 4 square. Okay, so just by substituting n over 4 to the original equation, we will be able to obtain what is 3n over 4. Therefore, what we are going to say now is, instead of tn over 4, we can actually have c n over 4 square, and then we will have 3 other branches, each of t n over 16. Okay, so that is what we are doing here. So c n over 4 square, and then each branch will have t n over 16, t n over 16, t n over 16 3 times, and the same thing here, and the same thing here. We're going to do it, let's say, one more time, just so that we are sure what is happening. We will talk about the cost in a moment. But the cost actually is very easy to see, because, for example, here the cost is cn square. What can you say is the cost of this second level here? It's going to be 3 times c n over 4 all square. Okay, so this is the cost of this second level. Before we look at the third level, let's try to expand one more time to see what we will have. So now I have, instead of n, I have n over 16. So what is t n over 16? Clearly it's going to be 3 t n over 16 over 4, which is essentially n over 64, if you like, because 16 times 4 is 64. Another way to look at it as 4 cubed, actually. So we can look at we can look at that way as 4 to the power 3. Okay, so it's going to be n over 4 to the power 3 plus c n over 16 square. So this is what we have. Therefore, what this means is that instead of this tn over 16, okay, each of this will be c n over 16 square, and then another 3 branches, each of t n over 4 cubed. Okay, t n over 4 cubed, t n over 4 cubed. Each of these terms can be represented like that. So the question is, what is the cost of this level? This is what it will look like. It's 3/16 square cn square. Now, if you observe, there is clearly a pattern here. First one is cn square, then 3/16 cn square, 3/16 square cn square. If you think of this as 3/16 to power 0 cn square, we know anything to power 0 is 1. Okay, so this is 3/16 to power 0, this is 3/16 to power 1, and this is 3/16 to power 2. The next one is going to be 3/16 to power 3 cn square, and so on. So in general, when we reach the depth of the tree, we're going to have 3/16 to power d cn square. Okay, when we reach depth d, this is what we're going to have. This will allow us to estimate the cost of each level. So we now just need to add all of this to see what we have. Yeah, this is what we have just answered actually. What is the cost of each level? Each level, as we see here, is 3/16 to power the level number, assuming we start counting from 0, times cn square. This is the cost of each level. Now clearly this is different from what we saw in the merge sort, because in merge sort each level costs the same, but here the levels are costing differently. Right, so this answers our first question, because remember we have 3 questions to answer. 1, what is the cost of each level? 2, what is the depth of the recursion? And 3, how many leaps are we going to have? So first question answered, we can clearly see the cost of each level. So for the depths, you have to notice that we keep dividing by 4. Okay, so initially it was n, then we divide the input size by 4. Okay, then we're going to divide by 4 again, and by 4 again, and so on. So in summary, by the time we reach level D, we will have each size will only be n/4 to power d, because we started by dividing by 4, then 4 square, then 4 cubed, and by the time we reach d, it's going to be 4 to power d. This is how the input size is being divided. Now this will actually help us to know what is the value of d, what is the level of the tree, or what is the depth of the tree, because we know that this dividing of n cannot go indefinitely. There will be a point where we reach 1. Okay, we saw that with the merge sort. So if that is the case, when n divided by 4 to power d is equal to 1, what is the value of d? So this is very easy to find now. We just need to take the log of both sides. Okay, there are 2 ways to do it. You can do it like this, or you can simply say based on this, n is equal to 4 to power d, and therefore take the log of both sides. You have log n here, and here you have log of 4 to power d. So assuming you are taking log to base 4, okay, this of course will be d log of 4 to base 4, and therefore this is 1, so d is actually going to be log of n to base 4. Okay, alternatively, if you just do it like this, log of 1 of course is 0, but log of a over b is the same as log of a minus log of b, so d log of 4 is going to be log of n, and therefore d is log of n to base 4. Okay, the same way. So we now know the depth of the recursion, which is the second question we must answer. If we know the depth of the recursion, all we have to do now is to sum up the the cost of each level for this number of levels to know the total cost of the running time function. But there is one more thing we have to do. The last level, we have to estimate we have to know what are the number of leaps in that level. Of course, we know that in the last level, we will have 1. T of 1 is obviously constant. So the issue is not the T of 1 itself. The question is how many of it are we going to have? How many leaps? Each leap will cost T of 1, which is constant. But how many leaps? Those number of leaps may depend on n. So we cannot rule it out as simply a constant. We have to evaluate it and see. So this is what we are trying to do here. How many leaves are there in the complete ternary tree of depth d? Clearly, it's going to be 3 to the power d of them, because as you can see, we have 3 to the power 0, which is 1 in the level 0. We have 3 to the power 1 terms in level 1. Okay, 3 to the power 2, which is 9 in the second level. So when we reach d, we're going to have 3 to the power d. But we have just computed our d. It is actually log of n to the base 4. And therefore, there are going to be 3 to the power log of n to the base 4 leaps in the last level, each of which is constant. Alright, so with this we are now ready to represent our running time function. So the running time function Tn is going to be the root, which is Cn square, plus 3 over 16 Cn square, and so on, until just before the last term. Okay, it's going to be the same way, but for the last level, we will represent it as theta of 3 to the power log of n to the base 4, because we know there are this number of them. Okay, good. So this is the equation we need to try and simplify. There's a lot of mathematics involved, but I think if you follow, it should be easy to see what is going on. So first of all, clearly, as I showed you earlier, this Cn square can also be represented in the same way. It's simply 3 over 16 to power 0 Cn square, because to power 0 is 1, right? So that will allow us to do the summation of the same term, for I from 0 until d minus 1. Okay, so for I from 0, 1, 2, and so on until d minus 1 is the same term, and 3 over 16 I. Okay, so I initially is 0, then 1, then 2, and so on until d minus 1. So we can represent all of those as this. Of course, Cn square is common in all the terms, so we can factor it out. So Cn square is factored out. All we have to do is sum up this 3 over 16 to power I, for I from 0 until d, but d is until d minus 1 rather, but d is log of n to the base 4. So this is the summation we have, plus the elements in the last level, which is theta of log of n to the base 4. Now, there is a very similar summation actually to this that can allow us to simplify this, which is summation of I from 0 to infinity. Now clearly, instead of just stopping until I is equal to this value, if we continue until infinity, then the result we're going to get is going to be bigger than what we have here. Okay, remember, in big O, we're not interested only in equality. The inequality is good for us. So if we can extend this to infinity, it will actually allow us to do more simplification. So if we extend to infinity, the result we will get definitely will be bigger than what we have here. And now, if you check, there is a summation, there's a document I put in the Blackboard which gives some common summation formulas. Now one of them will allow us actually to simplify this term. It says summation of x to power k, provided x is a fraction less than 1. And we have less than 1 here. 3 over 16 is less than 1. It's a fraction. If you do that until infinity, it will be the same as 1 over 1 minus x. Alright? So this is a very useful formula that will allow us to simplify this. So now, it means if we replace our, if we substitute our 3 over 6 with x, we will have this simple representation of the summation. So we're going to have 1 over 1 minus the x. Well, the x in our case is 3 over 16, cn squared. Now if you do the subtraction, let's try and do it quickly. 1 minus 3 over 16, what is it? Well, the LCM is 16, and here we will have 16 minus 3. So this is 13 over 16. So basically we have 1 divided by 13 over 16. Clearly this is going to be 16 over 13. Yani 1 over 13 divided by 16 is the same as 16 divided by 13. Okay, so this is how we reduce this term to 16 over 13 cn squared plus theta of 3 log of n, 3 to power log of n to base 4. So we are almost done, Shabab, because this is very much what we want, cn squared. But we have to rule out that this term is less than cn squared before we can make that conclusion. Because we have got a c here, because this multiplied by c is still a constant, and we have n squared. So we are almost there, but we need to make sure this term, because it involves n, we cannot just discard it. It involves n, so we have to go and evaluate it further to see what exactly is 3 to power log of n to base 4. Is it going to be bigger than cn squared or not? If it's going to be less, then we can eventually discard it. But for now, we don't know. We have to simplify this further. This is what is left for us, which we will do in the next slide. Yeah, so this is what I'm asking here. What does this mean actually? Okay, so to simplify this, we need to remember some properties of log. Particularly, we have to remember that the log and the power function are reciprocal. Okay, yeah, so a is the same as b to power log of a to base b. All right, yeah. There's also another term here which will be helpful later. So this again, I posted a document in Blackboard showing you some of this logarithmic feature which you should all know from your basic maths. So we should remember some of these logarithmic functions. Now, so let's see what we can do based on this to simplify this term. We can straight away say that 3 to power log of n to base 4 can be represented as 4 log to base 4 of the same term. Okay, yeah, because log and power, they are reciprocal. So if we take log to base 4 and then raise to power 4, we are just cancel, they will cancel out. We will still end up with the same term we started here, 3 to power log of n to base 4. I hope this is clear. Because the idea is we want n to be the main thing here in this expression. We don't want 3 to power log of n. Can we represent it as n to power something? This is our target. Is there a way we can represent this as n to power something? And that's what we are trying to do here. So this can be represented as this. There's nothing new here. It is just the same term here. We are only raising the power and also taking the log. So this will cancel each other because taking the power and taking the log, they are reciprocal. So here we have log of 3 to power something to base 4. Clearly we can take this and multiply it with the log, as we all know. Right here, for example, log of a to power n to base b is the same as n times log of a to base b. So that is just what we are doing here. Take the log of n to power 4 and multiply it with that. And this is what you have. Good. Now we're going to do the reverse. Okay, the reverse of what we have just done. But this time, taking this to be the power. Okay, so this is equal to 4 to power log of n to base 4 all to power log of 3 to base 4. So raising this to the power. Very good. So now we are again going to do the reverse of what we did initially. Instead of saying to power 4 and then log of 4, we can actually just say it is equal to n log of n to power log of 3 to base 4. And that is exactly what I have here. So this whole thing here can be said to be n to power log of 4 to base 3. And this is more like what we want, because you see these are now constant numbers. The power here is a constant number. And actually it's going to be less than 1, because we know that log of 4 to base 4 is 1. But this is 3. It is less than 4. So this is definitely less than 1. Okay, it's going to be 0 point something. So basically we have n to power 0 point something. You can compute it and see what is log of 3 to base 4. Alright? Good. And that is actually what we want, because now we know this n is really less than n squared. So we can therefore ignore it and just concentrate on our the term with n squared. Yeah, so that's what I have here. Tn, remember it is this, but we have just shown that that right hand side, 3 to power log of n to base 4, can actually be represented simply as n to power log of 3 to base 4. And clearly now we can eliminate and say it is simply big O of n squared, because the n squared is the term with the higher degree. This degree is less than 1 even. Okay, so we can ignore it and say Tn is big O of n squared. So after all this mathematics, this is what we are able to achieve, that our running time is big O of n squared. But this is not the end of the story. Remember, the recursive tree method is not conclusive. We still have to use substitution method to prove it. This is what we do next. So going back to our equation, 3n is equal to 3tn over 4 plus n squared. We now need to prove that it is big O of n squared. So we're going to make a hypothesis that it is true for k less than n. Okay, so tk is going to be big O of k squared. If it is true for k less than n, it definitely is true for n equal to n over 4. So substitute n over 4, and we will have t of n over 4 will be big O of n over 4 all square. And that means we can actually represent it as a constant c times n over 4 square. And the tn over 4 will be less than or equal to c that, based on the definition of big O. So now it is this we are going to substitute back into our tn. Instead of this tn over 4, we will have cn over 4 all square. So if we do that, we will have, instead of this tn over 4, we have cn over 4 square. So finally we are able to eliminate the t from the right hand side. What we now need to do is to simplify this to make sure it can be in the form of cn squared. So if you expand this, this is going to be 3 over 16 cn squared plus n squared. So finally our cn squared is coming out. The question is, when can we say this is less than cn squared? Because that's what we want. When is 3 over 16 cn squared plus n squared going to be less than or equal to cn squared? So let us try and simplify this. First of all, let us collect the terms with c together. So we're going to bring this cn squared back to the left side and take the n squared to the other side. So we will have 3 over 16 cn squared minus cn squared is less than or equal to minus n squared. If you multiply by minus 1, we will have cn squared minus 3 over 16 cn squared will be greater or equal to n squared. Now factor out the cn squared. So cn squared, you will have 1 minus 3 over 16 on this side, greater or equal to n squared. Okay, what is this value? I think we computed it before. It is 13 over 16 if I remember. Okay, 1 minus 3 over 16, the LCM is 16, and we're going to have 16 minus 3, which is 13 over 16. Okay, so what we have is cn squared times 13 over 16 is greater or equal to n squared. Therefore, what can you say is c? C will be greater or equal to n squared times 16 divided by n squared times 13. So n squared will cancel n squared, and c will be greater or equal to 16 over 13, which is definitely a positive number. In other words, our inequality Tn less than or equal to cn squared will be true if c is greater or equal to 16 over 13. And therefore, by the definition of big O, Tn is clearly big O of n squared, because we are able to find a positive constant c that satisfy this inequality Tn less than or equal to cn squared for n greater or equal to 1, for example. So that is basically the proof. That shows you how to solve recurrence relation using the recursive tree method.